Welcome to Deep Thinkers. Settle in. Let your shoulders drop away from your ears, let the weight of the day loosen its grip on you, and let your breathing find its own slow rhythm without you having to do anything about it at all. There is nowhere to be tonight. Nothing to solve. No decision waiting for you on the other side of this. You can let all of that go now, gently, the way you might set down a bag you have been carrying so long you forgot it was heavy. Tonight, we are going to think about something that is happening right now. Quietly, beneath your bed, beneath the floor, beneath the deepest foundations of the deepest building anyone has ever raised. Thousands of kilometers below the place where you are lying still, there is a slow and enormous thing turning over in the dark. It has been turning for billions of years. It will keep turning long after this night and the next, and every night either of us can imagine. And it is the reason a compass needle knows which way to point. Here is the strange little truth we will begin with, and I want you to hold it loosely, the way you would hold something delicate you found on a walk. When you pick up a compass, and the needle swings, and the painted red tip settles toward the top of the world, you would say it is pointing north. Everyone would say that. It is the most ordinary fact in the world, printed on the face of the instrument itself. North, and yet the thing that is pulling on that needle, the thing at the far end of the world that is doing the attracting, is, by every physical definition we have, a magnetic south pole. A magnet's north end is drawn toward a south. That is simply how magnets behave. So the red tip that points you north is being tugged faithfully towards something that is physically the opposite of its name. The names, you see, are ours. North and south, the way we mark them on a compass, on a map, on the little dial in a car, are a human convention, a decision made long ago for our own convenience, so that the tools would agree with one another. The Earth never signed off on it. The Earth does not know it is being called north. And every so often, without asking anyone, without warning, without any regard for the maps we have drawn or the words we have written across them, the Earth changes its mind. The whole thing flips. What we call north becomes south, and what we call south becomes north, and a compass needle that pointed you faithfully toward the top of the world for your entire life would slowly and then completely come to point the other way. Not because it broke, not because you were holding it wrong, but because the planet itself turned its great magnetic body over in its sleep. This has happened before, not once, not twice, hundreds of times, and that is what we are going to sink into tonight, slowly, one gentle layer at a time, not as a warning, not as something to be afraid of in the dark, quite the opposite. It is one of the most reassuring stories the Earth has to tell once you understand its true size and its true slowness, and how many times life has already ridden through it and come out the other side, blinking, unbothered, carrying on. Before we go down into the core of the world, into the ocean of molten iron that makes all of this possible, let me ask you something, the way I like to at the start of these long, slow journeys. Wherever you are listening from tonight, whatever country, whatever city, whatever quiet room, I would genuinely like to know. If you feel like it, leave a word in the comments telling me where in the world you have carried this story tonight. It is a strange and lovely thing to think of so many people in so many different places, all lying still beneath the same wandering magnetic field, all being pointed north by the same slow machine. And if you are new here, if this is the first of these you have found, You might quietly hit subscribe so the next slow story finds its way to you when you need it. But you do not have to do any of that now. You do not have to do anything now. That can wait for the morning, or for never. Tonight you can simply listen. Because we are going to take this one slowly, all the way down. We are going to build, piece by piece, an understanding of why a compass points at all. What is actually happening at the heart of the planet to make that little needle swing, and why that same heart, every so often, decides to turn the whole arrangement upside down. There is no rush. If you fall asleep before we reach the seafloor striped like a barcode, or the sky that filled with strange radiation 40,000 years ago, that is not a failure. That is exactly the point. Let the words become a kind of tide, coming in and going out, and let yourself drift off somewhere in the middle of them. The story will still be here. The earth will still be turning it over, patiently, whether either of us is awake to watch or not. So, let us begin the descent. Imagine you could sink. Not fall, not plummet, nothing sudden or frightening. Just sink, slowly and safely, straight down through the floor beneath you, the way a stone settles through still water. Down through the carpet and the boards, down through the foundations, down past the pipes and the buried cables and the roots of the oldest trees. Down through the soil, and then through the rock beneath the soil, the cool grey bedrock that holds up everything we have ever built. You keep sinking. The rock grows warmer around you. This is the crust, the thin, cool skin of the world, and it is astonishingly thin, thinner in proportion than the skin on an apple. You pass through it far sooner than you would expect, and then you enter the mantle, a vast, slow, hot region of rock that behaves, over enormous spans of time, almost like a thick fluid, churning so gradually that a single loop of its motion can take longer than the age of the mountains. Down and down. Hundreds of kilometers. 1,000, the heat and pressure would be beyond anything we can truly picture, but you are only imagining, and imagination sinks freely, so keep going. And then, at last, about 2,900 kilometers below where you started, about 2,890 kilometers down to be a little more exact, the solid world gives way. The rock ends, and you slip into an ocean, not an ocean of water, an ocean of metal. Molten iron and nickel, liquid, glowing, moving, this is the outer core, and it is enormous, a shell of liquid metal wrapped all the way around the center of the earth, and it is roughly 2,200 kilometers thick. Sit with that for a moment. 2,200 kilometers of molten metal. More than the distance across many entire continents, all of it liquid, all of it in motion, all of it beneath your feet right now as you lie there in the dark. If you were to sink into it, you would be swimming, if such a thing were possible, through a sea of liquid iron thicker than the whole width of a country, glowing with a heat that has been trapped inside the planet since the world was young. This molten sea is where the magnetism is born. This is the engine, this is the thing that is quietly, endlessly, keeping your compass true. But let us not stop at the outer core, because there is more below it, and it is one of the most wonderful facts in all of this. If you kept sinking down through the 2,200 kilometers of molten iron, you would eventually reach the very center of the world, and there you would find something you might not expect. The metal becomes solid again. At the heart of the earth there is a ball of solid iron, the inner core, and it has a radius of about 1,220 kilometers. That is slightly smaller than the moon. Picture that, if you can, as you lie there. At the center of the planet, held in the middle of that ocean of liquid metal, there is a solid iron ball very nearly the size of the moon, and it is one of the reasons your compass works at all. Now here is the puzzle that makes people sit up when they first hear it, though I hope tonight it will only make you sink a little deeper into your pillow. That inner ball is solid. The ocean of iron around it is liquid, and yet the inner ball is hotter. The very center of the Earth is the hottest part of the whole planet. So how can the hotter thing be solid while the cooler thing around it is liquid? Everything in your everyday experience says heat melts, heat loosens, heat turns solid to liquid, ice to water, wax to a pool. So how does the hottest place of all stay frozen solid? The answer is pressure. Down there, at the very center, the weight of the entire planet is pressing inward from every direction at once. The whole mass of the world is squeezing down on that iron ball, and that unimaginable pressure changes the rules. Pressure raises the temperature at which iron freezes. It packs the atoms so tightly together that even at those searing temperatures they cannot break free and flow. They are held in place, locked, solid, not because it is cold, but because it is crushed. The inner core is frozen not by cold, but by pressure, and the outer core, further out, where the pressure is a little less crushing, stays liquid, free to move. And it is that movement, that slow churning of the liquid metal ocean, that makes all the magic happen. Let me try to give you a feeling for it, gently, without any hurry. Heat is escaping from the center of the Earth. It always has been, ever since the planet formed, a great store of warmth trapped inside, leaking outward through the ages. And heat, when it tries to escape through a fluid, sets that fluid moving. You have seen this in a pot of water on the stove, the way the warm water rises from the bottom and the cooler water sinks to take its place, curling over and over in slow rolls. That rising and sinking has a name. It is called convection. And the outer core, that ocean of liquid iron, is convecting on a scale almost too large to hold in the mind. Hot metal rising, cooler metal sinking, vast slow loops of molten iron turning over and over in the dark. There is a second engine driving that motion too, and it ties back to that frozen ball at the center. The inner core is not fixed in size. It is slowly, slowly growing. As the Earth very gradually loses its heat over the ages, the liquid iron at the bottom of the outer core freezes onto the solid inner core, adding to it, atom by atom, thinner than any layer you could ever see, over spans of time longer than you can feel. And here is the lovely part. When iron freezes down there, it does not freeze pure. The lighter elements mixed into the molten metal do not want to join the solid ball. They are cast off, left behind, and being lighter than the iron around them, they rise. They float upward through the liquid ocean like the slow release of something buoyant rising through deep water. And that rising of the lighter stuff stirs the whole ocean even more. This is called compositional buoyancy, which is only a careful way of saying that the freezing at the center squeezes out the light material, and the light material floating up keeps the whole sea churning. So you have this vast ocean of molten iron, kept in constant, slow, powerful motion by two things at once. The heat escaping from below, and the light elements rising as the inner core freezes and grows. Turning, turning, endlessly turning. But moving metal alone is not enough to make a magnetic field. There is one more ingredient, and it is the spin of the Earth itself. The whole planet is turning, once a day, the same turning that brings us the sunrise and the sunset, and every night like this one. And that spin reaches all the way down into the molten core and takes hold of the churning metal. When something is moving across the surface of a spinning world, its path gets bent, twisted to one side, deflected by the turning of the planet beneath it. This bending is called the Coriolis effect. It is the same influence that gives great weather systems their spiral shapes. The slow curl of storms seen from above. And down in the outer core, the Coriolis effect takes those rising and sinking columns of molten iron and twists them, rings them into long turning coils, organizes the churning ocean into great spiraling flows, all winding in a related direction. And now, finally, we have everything we need. Because that liquid iron is not just any fluid, it is metal, and metal conducts electricity. When you take an electrically conducting fluid and you set it moving and you twist that motion into organized coils by the spin of the world, you generate electric currents flowing through the metal. And electric currents flowing in coils produce a magnetic field. And here is the beautiful, almost circular heart of the whole thing. That magnetic field, once it exists, acts back on the moving metal, guiding it, sustaining the very currents that created the field in the first place. The field helps make the motion that makes the field. Round and round, feeding itself, holding itself up by its own effort, needing nothing from outside but the heat leaking from the core and the steady turning of the planet. We have a name for this self-sustaining engine, this machine that generates a magnetic field out of nothing but molten metal, heat and spin. We call it the geodynamo. Geo for the Earth. Dynamo for the generator. The geodynamo. A generator the size of the moon and larger, running silently at the center of the world, powered by the slow freezing of iron and the ancient warmth of a young planet, and it has been running, in one form or another, for billions of years. And that, at last, is the answer to the very first small question we asked. Why does a compass point at all? Why does that little needle know which way to swing? Because thousands of kilometers beneath it, an ocean of liquid iron is turning in the dark, twisted by the spin of the world, generating a magnetic field that reaches all the way up through the mantle, up through the crust, up through the floor and the boards and the carpet, up into the room where you are lying, and gently, invisibly, takes hold of that needle and turns it toward the pole. Every compass that has ever pointed north was being guided by a freezing ball of iron the size of the moon and the molten sea around it. The most ordinary instrument in the world, quietly obedient to the most extraordinary machine there is. Now the field that this great engine produces reaches up and out beyond the compass, beyond the room, beyond the sky. If you could see the shape of it, the overall shape of Earth's magnetic field, it would look, more or less, like the field around a simple bar magnet. The kind of magnet a child plays with, the kind that pulls iron filings into those graceful curving lines that arc from one end to the other. Earth behaves, in its broadest strokes, as though a colossal bar magnet were buried inside it, running roughly from pole to pole. Scientists call this the dipole, which only means it has two poles, a north and a south, like the two ends of that toy magnet. But it is not quite aligned with the way the planet spins. The Earth turns around an axis, an invisible line running through the geographic North Pole and the geographic South Pole. The fixed points the whole globe rotates about. And you might expect the magnet inside to line up perfectly with that spin. It does not. The magnetic dipole is tilted, leaning off from the spin axis by about 11 degrees. So the magnetic poles and the geographic poles are not in the same place. They never have been. When your compass points toward magnetic north, it is not pointing at the true top of the world, the point the planet spins around. It is pointing a little off from it, toward the tilted magnetic pole, and the difference between the two, the angle between where your compass points and where true north actually lies, is real enough that navigators have to account for it. They give that difference a name too. They call it magnetic declination. But hold that lightly. The thing to carry with you is only this. The great magnet inside the Earth sits at a slight tilt, about 11 degrees off from the way the world turns, and it is only a rough approximation anyway, because the true field is far more tangled and complicated than any simple bar magnet, full of smaller wrinkles and lobes that the neat dipole picture smooths over. And that field does something for us, up here at the surface, that is easy to overlook and impossible to overstate. It shields us. The sun is not a quiet neighbour. It pours out more than light and warmth. It throws off a constant stream of charged particles, a thin, fast wind of electrically charged matter blowing outward through the solar system in every direction. We call it the solar wind. And it never stops. Day and night, this wind of particles comes rushing toward the Earth and beyond it. From the deeper reaches of the galaxy comes cosmic radiation too, high-energy particles born in the violent places between the stars. All of it streaming toward us. But it does not reach us, not most of it, and the reason is the field. That magnetic field, generated by the churning iron core, reaches far out into space, well beyond the atmosphere, and it forms a great invisible shell around the whole planet. When the solar wind comes rushing in, the field deflects it, turns it aside, sweeps most of it around the Earth, the way a stone in a stream parts the water flowing past it. This protected bubble, this cavity that the magnetic field carves out of the solar wind, has a name of its own. It is called the magnetosphere, the sphere of magnetism wrapped around the world, holding back the storm from the sun. And it matters more than almost anything. Without that field, without that magnetosphere turning the solar wind aside, the atmosphere itself would be far more exposed to the erosion of all those charged particles, slowly stripped and worn away by the endless wind from the sun over the long ages. The air we breathe, the sky we live under, is sheltered in part by an ocean of molten iron thousands of kilometers beneath us. The freezing ball at the center of the Earth, the churning metal sea, the twisting coils raised by the spin of the world, all of it reaching up and out to hold a shield over the whole planet, over every living thing. Over you tonight, as you lie there safe beneath it. Take a moment with that before we go any further. You are lying still in a quiet room, and beneath you, straight down, thousands of kilometers of solid rock. And beneath that, an ocean of liquid metal turning slowly in the dark, and at the center of it all a frozen iron heart the size of the moon, and the whole vast machine is running, silently, without pause, generating an invisible field that rises up around the entire world and stands between you and the wind of the sun. It asks nothing of you. It does not need you to tend it or wind it or keep it going. It simply turns, and has turned, and will go on turning, and while it does, you are held. You are sheltered. You can rest. And yet, for all its steadiness, for all the billions of years it has been running, this great machine is not fixed. It is not a clock that keeps perfect time. It wobbles. It drifts. It has moods, if we can gently call them that, on timescales so long they make a human life look like a single breath. The magnetic poles are not nailed in place. They wander. The one we call the North Magnetic Pole, the place your compass needle reaches for, has been drifting for as long as we have measured it, moving slowly across the top of the world, from the Canadian Arctic and away toward Siberia, across the roof of the planet. And it does not even wander at a steady pace. Through much of the last century, it crept along at something like 15 kilometers a year. A slow shuffle you would never notice. But in more recent decades, it has been quickening, at times to 50 or 60 kilometers a year, fast enough that the people who keep the official maps of the field, who maintain what is called the World Magnetic Model, have had to update their charts ahead of schedule, hurrying to keep the maps honest as the pole slides on beneath them. But even that, the wandering pole, the drifting field, is only the small motion, the daily fidget of the machine. Because beneath the wandering, over spans of time so vast they can barely be spoken aloud, the geodynamo does something far stranger and far greater. Every so often, on no schedule that anyone can predict, it turns the whole magnetic arrangement over. North becomes south. South becomes north. The great tilted magnet inside the Earth reverses itself entirely. And a compass that pointed toward the Canadian Arctic, toward Siberia, toward the top of the world, would slowly, over the long centuries of the change, come to point the other way, toward the bottom of the world instead. The Earth changes its mind. We know this has happened. We are not guessing. The record is written into the stone of the planet itself, frozen into lava that cooled long ago and into the floors of the oceans, and once you understand how to read it, you can count the flips, one after another, back and back through deep time. Hundreds of them. And that is where we are going next, slowly, gently, in no hurry at all, to the fossil compasses locked in ancient rock, to the ocean floor striped like a barcode, each stripe a frozen photograph of which way north used to be, to the patient men who first found rocks magnetized backward and dared to wonder what it meant. But before we go there, let the picture we have built so far simply settle over you like a heavy blanket. The thin, cool crust, the slow, hot mantle, the 2,200 kilometers of molten iron beginning some 2,890 kilometers down. The solid inner core at the center, a frozen ball nearly the size of the moon, held solid not by cold, but by the crushing weight of the whole world pressing in. The heat leaking outward, the light elements rising as the iron freezes, the great slow convection of the metal sea, the spin of the planet twisting it all into coils by the Coriolis effect, the electric currents, the magnetic field feeding itself, sustaining itself, the geodynamo running on and on, the tilted dipole leaning 11 degrees off the spin of the world, the magnetosphere spread over everything, turning aside the solar wind, and the poles wandering, drifting, and every so often, without warning and without any schedule we can name, turning the whole thing upside down. There is no need to hold any of it firmly. Let the facts loosen and float. If you remember only the feeling of it in the morning, the feeling of that vast, slow machine turning beneath you in the dark, that is more than enough. The details will keep. The Earth is patient. It has all the time there is. For now, just notice how far down we have already travelled, you and I, from the quiet room where you lie to the very centre of the world, and how gentle the whole descent has been. Nothing sudden. Nothing sharp. Just a slow sinking through layer after layer, each one warmer and stranger and older than the last. until we reached the freezing heart of everything and found it quietly at work, keeping the compasses of the world pointed true. And it will keep pointing them true tonight, whether you are awake or not. That is the reassurance underneath all of this, the thing to carry down with you into sleep. The machine does not rest, so that you can. It turns so steadily that we can measure its wobbles in kilometers a year and its great reversals in the hundreds across the ages, and through every one of those reversals, through every wandering of the pole, life has gone on. The wind from the sun has been turned aside, the sky has been held in place, and a small needle somewhere has gone on swinging quietly toward a pole that is, by every physical law we know, the opposite of its name. Rest a while in that. We have hundreds of flips still to count, an ocean floor striped like a frozen barcode still to read, and an old collapse of the field 40,000 years ago still waiting in the dark ahead of us. But none of it is going anywhere. The story turns as slowly as the core that made it, and you are welcome to fall asleep anywhere inside it. So let the picture of the molten world go soft at its edges now. Let the glowing iron see dim to a warm and distant ember far below. Turning, let the great invisible shield settle over you like something kind. And let your breathing slow to match the slowness of the thing beneath you. The patient engine at the center of the earth that has never once, in all the ages of the world, stopped turning north into south, and south back into north, over and over, through all the long deep time there has ever been. We will follow those flips down into the stone next, and read them one by one. There is no rush at all. A reversal, when you first encounter the word, sounds violent. It sounds like something snapping, like a wire pulled too tight and suddenly cut, like the world lurching sideways in the night. But the word is misleading, as words often are when they try to describe something that unfolds over 1,000 years or more. A reversal is not a catastrophe. It is more like a very slow, very deep breath, the planet inhaling for centuries, the field growing confused and soft and strange in the middle of the breath, and then exhaling again on the other side, with north and south exchanged, and everything else more or less as it was. What it means, in purely practical terms, is this. The magnetic North Pole, the point toward which your compass needle swings, picks up and moves. Not quickly, not in a single season, not in a human lifetime, not even in the span of a civilization. It moves across centuries, wandering as the field in the outer core shifts and reorganizes beneath it. And at some point during that wandering, it crosses the equator, and what was north is now south. And what was south is now north, and the compass that would have told your ancestor to walk one way would tell you to walk the opposite. Everything else, the sky, the ground, the seasons, the warmth of the sun, remains. Only the invisible line, the great unseen architecture of the field, has rearranged itself. This is strange enough to sit with for a moment. The whole orientation of the compass, the whole northward tug that sailors and explorers and migrating birds have relied on for hundreds of millions of years, is not a fixed thing, but a habit of the planet. A very long habit, a very stable one most of the time, but a habit, not a law. And the planet has broken it before. Many hundreds of times it has broken it. The question that followed, once people began to suspect this was true, was not a simple one. You cannot simply go outside and watch a reversal happen, not in any single human life. The event is too slow, too deep, too geological for direct observation. What you need is a record a way of writing down which way north was pointing, not last year, not a century ago, but 1,000,000 years ago, or 50 million, or 150 million. And the Earth, it turns out, has been keeping exactly that kind of record, in a language that took human beings a very long time to learn to read. The record is written in stone. Specifically, in the iron-bearing minerals locked inside certain kinds of rock, and most vividly, most reliably, inside a mineral called magnetite. Magnetite is iron oxide, a natural compound of iron and oxygen that forms in the cooling magma of volcanoes and in the slowly compacting layers of ocean sediment, and it has a property that, once you know about it, seems almost impossibly convenient. When magnetite is hot enough, above a temperature called the Curie point, its tiny magnetic domains are free to rotate, pointing randomly in all directions, like a crowd of compass needles that have not yet decided where to stand. But as the rock cools below that threshold, those domains freeze. They lock into alignment with whatever magnetic field is present at that moment, and they stay there, held in place by the crystalline structure of the cooling mineral, for millions and in some cases hundreds of millions of years. The rock becomes, in that moment of cooling, a fossil compass, a permanent record written in iron of which way north was pointing on the day the lava hardened or the sediment settled into stone. This phenomenon has a name. It is called remnant magnetization, or paleomagnetism, palaios being the Greek word for ancient, and it is one of the most quietly remarkable tools in all of geology. Every lava flow that has ever cooled on the surface of the Earth carries within it, if you know how to read it, a direction, a heading, a tiny preserved note from the past saying, "On this day, in this place, north was here." And the scientists who learned to read those notes found something that changed everything they thought they knew about the planet. They found that many old rocks point the wrong way. Not wrong in the sense of a measurement error, not wrong because of some confusion in the laboratory, but wrong in the deepest possible sense, pointing in precisely the opposite direction from the present field, with a consistency and a geographic spread that cannot be explained by anything except one thing. At some point in the past, when those rocks were cooling, north and south had exchanged. The field had reversed. And the rocks, faithful instruments that they are, had recorded it without comment, without alarm, simply locking in the field as it was and carrying that information forward through all the subsequent ages until the moment someone thought to measure it. The scientist most often credited with first finding those wrong-pointing rocks was a Frenchman named Bernard Brunhes, and the year was 1906, and the place was a village called Pontfarrain, in the ancient volcanic country of the Massif Central in southern France. Brunhes was examining the magnetization of ancient lavas and the fired clay beneath them, the ground itself, baked hard by old volcanic heat, and he found that the rocks near Pontfarrain had magnetized in a direction opposite to the present field. He concluded, carefully and with evident awareness of how extraordinary the claim was, that the field itself must have been reversed at the time those rocks cooled. Not that the rocks had somehow rotated, not that there was some local anomaly, but that the entire global field had pointed the other way. It was a radical idea, and it was not immediately accepted. The Earth's magnetic field reversing entirely, north becoming south, south becoming north, sounded, to many scientists at the turn of the 20th century, like the kind of claim that would require far more than a few oddly magnetized boulders in the French countryside to substantiate. More evidence came, slowly, from more places. and from another geologist who was working on the same problem a decade and more after Brunhes. His name was Brunhes-Matuyama, a Japanese scientist working in the 1920s, and what he contributed was not just additional reversed rocks, but the beginning of a chronology. Matuyama examined basalt samples from Japan and Manchuria and Korea, and he noticed something that Brunhes had not fully established. The reversed rocks were systematically older than the normally magnetized ones. The older the lava, the more likely it was to point the wrong way, and the younger the lava, the more likely it was to point the way a compass points today. This was not an accident. This was a pattern, and the pattern meant something. If the reversed rocks were always older and the normal rocks were always younger, then the field must have switched from reversed to normal at some point in the geological past, and everything before that switch would carry one polarity, and everything after would carry the other. Matuyama was reading a timeline in the magnetism of the Earth itself. He was not just finding reversed rocks, he was finding the boundary between two ages of the field, a geological clock face written in iron and stone. The chron that bears his name, the Matuyama chron, refers to the reversed polarity epoch that preceded our own, and the boundary between it and the Brunhes chron that we currently inhabit, the moment when the field last completed a full reversal, is dated to roughly 780,000 years ago. This is the Brunhes-Matuyama reversal, and it is the last time the compass flipped completely, the last time north became south and stayed that way. Everything since that boundary, all of human prehistory, the rise of modern Homo sapiens, every civilization, every navigation, every migrating bird that has ever found its way, has happened inside the Brunhes chron, the long, stable, normal period we still live within. But all of that understanding, the full weight of the reversal chronology and what it meant for the history of the planet, only fully arrived later, and it arrived from a direction that almost no one had anticipated. It arrived from the seafloor. Quick reminder, after years of lying awake with a racing mind, deep sleep finally became possible. Now learning comes easier, energy is real, and the mind stays sharp. Sleeping like a baby changed everything. If you want the exact system that made this possible, check the link in the pinned comments. The deep ocean floor is not empty. Flat and cold and dark as it is, unlit by any sun, pressed under kilometers of water, it is not a blank. It is, in fact, one of the most detailed archives of the planet's history that we possess. And it is written, like the lava fields of France and Japan, in the magnetic memory of iron. But what the ocean floor records is something even more remarkable than what Brunhes and Matuyama found on land, because the ocean floor does not just preserve individual moments of the field's direction. It preserves the sequence of all the moments, laid out in order, side by side, in stripes. To understand the stripes, you need to understand how the ocean floor is made. At the center of every ocean basin, running for tens of thousands of kilometers like an enormous undersea mountain range, there is what is called a mid-ocean ridge, a long chain of underwater volcanoes where the tectonic plates on either side of the ocean are slowly pulling apart. As the plates separate, molten rock rises from below to fill the gap, cooling into new crust, hardening into basalt, and then being pushed sideways, very slowly, centimeters a year, as even newer rock rises to take its place at the center. The ocean floor is being continuously manufactured at these ridges and continuously spread outward, a process called seafloor spreading, and it has been going on for hundreds of millions of years. And as each new strip of basalt cools at the ridge and is carried away to the sides, it does what cooling basalt always does. It locks in the magnetic field as it is at that moment. If the field is in a normal polarity, pointing the way our compasses point today, the new crust records that. If the field is in a reversed polarity, north and south swapped, the new crust records that instead. The result, spread across the ocean floor over geological time, is a pattern of alternating bands. A strip of normally magnetized rock, then a strip of reversed rock, then normal again, then reversed, laid down one after another as the seafloor spread outward and the field periodically changed its mind. And because the spreading is symmetric, new crust pushed equally to the left and to the right of the ridge, the stripes appear on both sides of the ridge as mirror images of each other. The same sequence of bands, the same widths, in the same order, reflected perfectly on either side of the volcanic center, like the pages of a book opened flat and laid face down on the floor of the sea. A barcode. That is the comparison that comes most naturally, and it is not inaccurate. If you could lift the ocean away and look down at the Atlantic floor, or the Pacific, or the Indian Ocean, you would see bands of rock striped in alternating magnetic polarities, running parallel to the ridges, symmetrical, ordered, a barcode pressed into the seafloor by the combined action of spreading plates and a reversing field, recording every flip the geomagnetic field has undergone for as long as the ocean has existed. The record goes back more than 160 million years in the oldest seafloor still preserved. Hundreds of reversals laid out in order, readable if you know the language. The people who first read that language, who recognized the seafloor stripes for what they were working in the early 1960s. And they arrived at their conclusion by measuring magnetic anomalies, variations in the strength and direction of the field measured from ships towing magnetometers across the ocean surface. These measurements had been accumulating since the 1950s, and they showed a pattern that puzzled the researchers examining them. The ocean floor seemed to be alternately more and less magnetic than expected, in long bands that ran parallel to the mid-ocean ridges. The pattern was there in the data, clearly visible, but its meaning was not immediately obvious. The explanation came in 1963 in a paper by two British geologists, Vine and Drummond Matthews, working with measurements from the Carlsberg Ridge in the Indian Ocean. Their argument was elegant and, once stated, almost obviously correct. The alternating stripes of higher and lower magnetism were produced by exactly the process described above. New oceanic crust, locking in the current field polarity as it formed at the ridge, then being spread to the sides, carrying its frozen magnetic signature with it. If the field had reversed many times in the past, and if the ocean floor was continuously being created at the ridges and pushed outward, then the floor would inevitably carry exactly this kind of striped, symmetric record of the field's history. A Canadian geologist named Lawrence Morley had come to essentially the same conclusion at roughly the same time, submitting his own paper earlier in 1963, but his paper was rejected by two journals before Vine and Matthews published, an episode that has earned a rueful place in the history of science as one of the more costly editorial misjudgments of the 20th century. The hypothesis is often called the Vine-Matthews-Morley hypothesis now, a three-name credit that acknowledges both the independent arrivals and the delay of recognition. What the Vine-Matthews-Morley hypothesis did, when it was accepted and confirmed by further measurements over the following years, was not simply explain some stripes in the ocean. It did something far more consequential. It provided, for the first time, decisive evidence that the continents were moving, that the ocean floors were spreading, that the plates were real. that Alfred Wegener's idea of continental drift, dismissed and mocked for decades, was not fantasy, but fact. The magnetic stripes and the reversal chronology and the mechanics of seafloor spreading locked together into a single coherent framework that became plate tectonics, the foundational theory of modern geology. The reversals of the magnetic field and the movement of the continents confirmed each other. You could not explain one without the other, and together they explained both. The compass had been flipping for millions of years, and the ocean floor had been recording it, and the record, once read, turned out to be the proof of something else entirely. Something about the way the whole surface of the planet was organized, and had always been organized. A frozen diary of one thing became the key to understanding another. It is worth pausing here, in the unhurried dark, to let that sit for a moment, because there is something remarkable about the fact that a question about the direction of north led, eventually, to the discovery of how continents move. The two things seem unrelated. A compass needle and the drift of South America away from Africa over 100 million years. These feel like they should belong to entirely different sciences, different conversations, different rooms. But they are, it turns out, bound together by the same mechanism. The same cooling rock, the same frozen iron minerals, faithfully pointing wherever north happened to be on the day they solidified. The compass is a window not just into the magnetic field, but into the deep architecture of the Earth's surface, the slow waltz of the plates. And the people who built the knowledge that made this discovery possible were working with instruments and questions that went back centuries before the ocean floor was ever surveyed. The human relationship with magnetism, with the compass needle and its northward bias, is a long one, and somewhere near its beginning, near the beginning of its scientific examination rather than its practical use, stands a book published in London in the year 1600, written by a physician named William Gilbert. Gilbert was the personal physician to Queen Elizabeth I, a man of considerable learning and considerable caution, and he spent 18 years performing careful experiments on magnets before he published what became the first serious scientific treatise on magnetism in the history of the Western world. He called the book De Magneti, On the Magnet, and it argued something that, for his time, was a significant intellectual leap. Gilbert proposed that the Earth itself is a great magnet. Not that the Earth contained a magnet, not that some external influence was pulling the compass needle north, but that the planet as a whole behaved as a magnetic body, with poles and a field, and that the compass needle responded to that planetary field just as a small magnet responds to a larger one. He built a model to demonstrate this. He carved a sphere out of lodestone, a naturally magnetic iron ore, and showed that a small compass needle behaved near the lodestone sphere in the same way it behaved near the Earth, pointing toward the poles of the sphere, dipping at different angles at different latitudes, responding to the sphere's field as though it were a miniature globe. He called his lodestone sphere the Torella, the little Earth, and with it he demonstrated, in physical, holdable, measurable terms, that the Earth's magnetism was not mysterious or supernatural, but mechanical, predictable, the product of the planet's own nature. De Magneti was a foundational document. It influenced scientists for generations. Galileo read it, and Francis Bacon read it. And the tradition of empirical investigation that runs through the whole subsequent history of physics owes something to Gilbert's insistence on demonstrating conclusions rather than merely asserting them. But Gilbert had no knowledge of the deep interior, no way of knowing what produced the planetary magnetism he had correctly identified. He knew the Earth behaved as a magnet. He did not know why, could not know why, because the tools and the framework for understanding what happens 2,890 kilometers below the surface would not exist for another 3 centuries. What Gilbert gave us was the question, framed in the right terms. What is the Earth's magnetism, and where does it come from? The answer, the molten outer core, the Coriolis twisted convection. The self-sustaining geodynamo took until the 20th century to assemble, and the discovery that the field reverses, that north and south have traded places hundreds of times in the history of the planet, came in the space between Gilbert's book and the present day, built from the combined work of geologists in volcanic fields and oceanographers dragging magnetometers across the deep water. Bernard Brunhes, working near Pontferrain in 1906, found the first reversed rocks and drew the correct conclusion, even though the mechanism was not yet understood and the idea met resistance. Brunhes-Matuyama, in the 1920s, extended the work across Japan and the Asian continent and established that the reversals followed a chronological sequence, older rocks pointing one way, younger rocks pointing another, a boundary between them somewhere in the geological past. And then, in the decades that followed, as instruments improved and ocean surveys became possible, the seafloor opened up its record and the stripes appeared in the data, and Vine and Matthews and Morley read them correctly. And the reversal chronology became not just a curiosity about a strange property of old volcanic rocks, but the backbone of a new understanding of the whole planet. The names of these crons, the Brunhes, the Matuyama, are not arbitrary labels. They are a small, human acknowledgement embedded in the geological timescale, a way of marking whose eyes first saw the evidence and whose careful thinking drew the right conclusion from it. When geologists say the Brunhes-Matuyama boundary, the reversal 780,000 years ago, they are reaching back through a century of accumulated understanding to the afternoon in the Massif Central when a French scientist held a compass near a piece of ancient lava and noticed that the needle pointed the wrong way. The stones had been waiting to be read for millions of years before that afternoon. They will go on carrying their record for millions of years after everyone who has ever measured them is gone. There is something very still about that, the patient mineral memory of the earth, indifferent to whether any creature ever notices it, recording north and south and the centuries between, layer by layer, stripe by stripe, as the slow work of the outer core continues far below. The stripes on the ocean floor, when you count them out in sequence, tell you not just that the field reverses, but how often. And the answer to that is more irregular, more strange, and in its own way more calming than you might expect. There is no clock running down here. No regular pulse, no countdown, no sense in which the Earth is waiting a fixed number of years between one reversal and the next. The intervals stretch and compress without apparent pattern, shaped by whatever is happening in the outer core at any given epoch, by the churning rhythms of convection and composition that are not yet fully understood and may never be fully predictable. Some intervals have been short, tens of thousands of years between one flip and the next, a geological eye blink. Some have been vastly longer, and one interval was longer than almost anything else in the record. Long enough to deserve its own name, long enough that the absence of reversals during it tells its own quiet story about the deep interior of the Earth during that time. That interval is still ahead of us in this account, as is the great record of reversals counted across the whole history of the seafloor, and the question of what happens to the field during the long centuries when it is neither one thing nor the other. Not cleanly normal, not cleanly reversed, but something messy and multiple. and strange, with poles wandering and the invisible architecture of the magnetosphere coming temporarily undone. All of that is still to come. For now, let the stones rest in their knowledge. Let the ocean floor lie striped and silent in the cold dark beneath all those kilometers of water, carrying its barcode record of every reversal since the ocean existed. Let the memory of Brunhes in the massive central, and Matuyama measuring basalt in Japan, and Vine and Matthews working through their ocean data in Cambridge, rest quietly in the background of what we know. The field has reversed many hundreds of times. The record is in the rock. The rock has been patient beyond any human measure of patience. And the story of those reversals, what they look like from inside one, how long they take, what the field becomes in the middle of a transition when it is neither normal nor reversed, but something altogether more complicated, is waiting just ahead, turning slowly toward us through the dark, the way everything in this story turns. There is no rush. The outer core is still turning. The stripes on the ocean floor are not going anywhere. And the question of what happens when the compass goes quiet, when the great invisible shield grows thin and the field forgets. For a time, where north is, that question has an answer, and the answer is older than any human memory, written in ice and tree rings and the slow accumulation of rare atoms in the atmosphere above a world that was. For a little while, briefly and temporarily unshielded. We will reach it. But the night is long, and the story is slow and careful, as all the oldest stories are. Let the seafloor stripes drift at the edges of your thinking now. Let the Atlantic dark and cold above all those kilometers of banded basalt, the mirror image record of every flip the field has ever taken, settle into something less like information and more like atmosphere, something felt rather than followed. The machine is still running. It has never stopped. And you are resting somewhere above it, very far above the molten iron and the frozen stripes and the patient minerals in their ancient stone, resting exactly as every creature has rested that has ever lived on the surface of this quietly magnetized world. Think about the number for a moment, not as a number, but as a weight. 183. That is how many full reversals have been catalogued in the past 83 million years alone. Not guessed at, not estimated by models running backward through probability. Counted, read directly from the rock, from the same magnetic stripes on the ocean floor that Vine and Drummond Matthews decoded in those early years of the 1960s, each stripe a chapter. Each boundary between stripes, the moment the field finally relented and turned over. 183 times, north became south. 183 times, a compass would have swung the other way, would have pointed toward what we now call the southern sky, toward Antarctica and the ice and the silence at the other end of the planet. And the planet survived each one. Life carried on, the oceans remained, the continents continued their long, slow migration. The sun rose and set above a world that was, for a span of centuries or thousands of years, navigating by a field that was confused about its own orientation, and none of it was catastrophic in any final way. None of it ended anything. It was simply the machine breathing. The record stretches back further still. Across the last 160 million years or more of geological time, hundreds of reversals have been identified in total, distributed unevenly across the deep archive of the past, some eras thick with flips and others stretching out in long, unmarked quiet. The irregularity is one of the most important things to understand about this process, because it is the quality that most confounds any intuitive sense of what to expect from the field. We are a species that likes patterns, that finds comfort in regularity, that builds calendars and schedules and tidal tables and eclipse predictions, and feels, rightly, that the universe is in many respects a place of lawful rhythm. But the geomagnetic reversal does not follow a rhythm. It has no beat. There is no interval you can reliably extract from the record and project forward. No frequency hiding in the data that would let you say, the next one is due in approximately this many years. The machine turns over when it turns over, driven by dynamics in the outer core that are themselves the product of convection patterns too complex and too deep to fully model or predict, influenced perhaps by events at the core mantle boundary where the molten iron meets the base of the solid rock above it, influenced perhaps by the slow drift of dense thermal structures in the lower mantle, influenced by processes we have not yet fully characterized. The compass flips when the deep engine reaches some internal threshold we cannot see, and that threshold is not evenly spaced in time. The intervals between reversals range across an almost incomprehensible span. Some have come as frequently as every few tens of thousands of years, clustered together like the fast pages of a book turning too quickly to read. Others have been separated by tens of millions of years, the same polarity holding steady for so long that entire orders of creatures rose and fell and were replaced by new ones without the field ever deciding to flip. There is no schedule. There is no average that functions as a due date. The common question, and it is an understandable question, one that arises naturally from the record, is whether we are overdue for a reversal, given that the last full one occurred approximately 780,000 years ago, and the historical spacing has sometimes been shorter than that. But average is not due date. The distribution of reversal intervals is not a normal curve with a predictable peak. It is irregular in the deepest sense, and the concept of being overdue implies a regularity the system has never shown. The field is not a train running on a timetable. It is a river finding its own way through changing terrain, and rivers do not keep schedules. 780,000 years. That is how long it has been since the last full reversal, the event known to geologists as the Brunhes-Matuyama reversal, a boundary in deep time that marks the end of one long chapter and the beginning of the one we are still living in. Some refined measurements place it closer to 773,000 years. The precision of modern geochronology narrowing what was once a rough estimate into something more exact, but the essential fact is the same. Nearly 800,000 years ago, the field completed a transition, and when it settled, the polarity that emerged was the one we have now. The one that points compasses northward, the one that has persisted through the entirety of human prehistory. Through the long patience of Homo erectus and the later emergence of our own species, through the ice ages and the interglacials, through the domestication of fire and the first ocean crossings and the slow accumulation of everything we now recognize as civilization. We have never known another polarity. Every compass ever made, every magnetic needle ever threaded onto a pin and floated in a dish of water by a medieval navigator, every declination ever measured, every deviation ever corrected for on a chart, all of it has operated within this single continuous polarity chron, this era of normal pointing compasses that geologists call the Brunhes chron. Named for Bernard Brunhes himself, the man who found the first reversed rocks near Pont-Ferrain in France in 1906, and could not have known, at the time, that he was standing at the edge of a discovery that would eventually rewrite the history of the planet. Before the Brunhes-Matuyama there was the Matuyama-Matuyama, named for Motonori Matuyama, the Japanese geophysicist who in the 1920s showed that rocks magnetized in the opposite direction from the present field were, systematically, older rocks, not anomalies, not errors, not local curiosities, but a global pattern pointing to an earlier time when the whole field ran the other way. The Matuyama itself was a period of reversed polarity that lasted roughly 2.5 million years, though it was interrupted by briefer episodes of normal polarity, temporary returns to the present orientation before the field reversed again. The crons nest within each other like that, long eras punctuated by shorter excursions and subcrons. The record complicated enough that reading it requires careful work and precise dating. But the essential outline is legible in the stone. The field has a history. It has been keeping this record for as long as there has been liquid rock cooling at the surface, for as long as magnetite has been crystallizing in cooling lava and sediment, and the record goes back hundreds of millions of years. Growing older and less precise with distance, but never entirely silent. What happens during a reversal, what the field actually does as it makes that long transition from one polarity to the other, is one of the questions the record has been slowly answering, and the answer is more interesting than any simple image of a compass needle swinging suddenly the other way. A reversal is not a switch being thrown. It is not a moment, it is a process, and that process unfolds over a span of time that is, by geological standards, quite brief. Geologists call such transitions geologically rapid, but by human standards is almost incomprehensibly long. The best current estimates, drawn from detailed sediment records and lava sequences, and the careful analysis of how quickly the magnetic signal changes in the rock, suggest that a typical reversal transition lasts somewhere between about 1,000 and 10,000 years. 1,000 years on the shorter end, 10,000 on the longer. The range is wide because the process is not identical every time, and because the precision of the record varies with the type and age of the material being studied. But even the shorter estimate, 1,000 years, is 40 generations of human life at present life expectancies. It is longer than all of recorded history. It is longer than the gap between us and the ancient Romans, longer than the distance back to the first writing, longer than everything we tend to call the modern world, and much of what we call antiquity besides. During those thousands of years, the field does not simply weaken and flip in an orderly way. It weakens, and as it weakens, it becomes something more complicated than a dipole. More complicated than the simple bar magnet approximation that describes the field in its stable phases. The dipole component, the dominant north to south pole alignment that makes compasses work reliably, fades, and as it fades, the non-dipole components of the field, which are always present but normally small compared to the dipole, grow relatively more prominent. The field becomes multipolar. It develops subsidiary poles, patches of reversed and normal flux scattered across the surface of the core, each one producing its own local magnetic structure at the surface. A compass does not know which way to point, because the field itself does not know what it is yet. It is in the process of becoming something new, and the in-between state is genuinely strange. If you could stand at different places on the Earth during such a transition and watch a compass, you would find it pointing in different directions depending on where you were, not subtly different. as magnetic declination causes compasses to deviate slightly from true north today. But radically different, meaningfully different. The kind of different that would make navigation by compass not merely imprecise, but actively misleading. A ship in the North Atlantic and a ship in the South Pacific, both using instruments of identical quality, might see their needles pointing in directions that differ by 90 degrees or more. The field overhead would be a patchwork, a complicated quilt of differently oriented magnetic patches rather than the relatively smooth dipole structure we navigate by now. For any creature that orients by the field, and there are many, from the migratory birds that detect magnetic direction through iron-bearing structures in their beaks and inner ear, to the sea turtles that use it to navigate across ocean basins with an accuracy that still astonishes researchers, to the bacteria that align themselves along magnetic field lines in ways so fundamental to their biology that they are named magnetotactic, the transition period would present a genuinely altered world, a world where the invisible map had become inconsistent and unreliable. And yet, life has passed through these transitions, all of it, repeatedly, without extinction. The record in the stone does not show mass die-offs aligned with reversals. No extinction event in the geological chronicle has ever been convincingly linked to a geomagnetic transition. The Brunhes-Matuyama reversal, the last one, the one that occurred 780,000 years ago, has been studied with particular care precisely because it is the most recent, the closest, the one for which the record is sharpest and most abundant. And that reversal passes through the fossil record without leaving any corresponding mark of catastrophe. Species were doing what they had been doing before it. The climates of the Ice Age cycles continued on their own orbital rhythms, governed by the geometry of Earth's path around the Sun rather than by the orientation of its magnetic poles. The ecosystems of the mid-Pleistocene carried on. The hominins of the time, early members of the genus that would eventually produce our own species, though not yet quite ourselves, continued to make stone tools and move across landscapes and manage the ordinary challenges of survival. They did not know the field was flipping. They had no instruments to detect it, no way to perceive the slow alteration of the invisible lines threading down through the planet beneath their feet. They simply lived, and the reversal happened around them over millennia, and when it was over, the world looked from the outside exactly as it had before, carrying nothing in the visible landscape to mark the enormous magnetic transformation that had completed itself in the dark of the outer core. This is the honest reassurance at the center of the reversal story. And it is important enough to let rest here for a moment, unhurried, before moving on. No reversal ever ended a world. The field has gone through this hundreds of times over the history of complex life on this planet, and complex life has continued. The magnetosphere does weaken during transitions, does allow somewhat more cosmic radiation to reach the atmosphere, does make the Van Allen belts less effective shields. But the atmosphere itself provides substantial protection against radiation. The column of air above any point on the surface offers shielding that the magnetic field supplements but does not fully provide. The transition may have consequences that are subtle and difficult to detect across the span of deep time, perhaps shifts in the rates of certain kinds of mutations in organisms particularly sensitive to cosmic radiation. Perhaps complications for magnetically navigating species. These are genuine questions. But the record does not support catastrophe. It supports survival. It supports the quiet persistence of life through conditions that are, by our present standard measures, abnormal but not deadly. There is another chapter in this story that points even more starkly at the dynamo's capacity for long stability, not in the direction of frequent reversal, but in the opposite direction entirely, the direction of almost impossible stillness. Buried within the Mesozoic era, within the long Middle Age of the dinosaurs and the pterosaurs and the early flowering plants, there is a stretch of geological time during which the field simply refused to flip. For approximately 40 million years, from around 120 million years ago to roughly 83 million years ago, the geomagnetic field held its polarity without a single full reversal. 40 million years. To put that in perspective, 40 million years ago, from the vantage point of today, the early ancestors of modern horses were small dog-sized animals browsing through forests that covered what is now the grassland of the American interior. 40 million years of elapsed time is longer than all of primate evolution. It is a duration that dwarfs everything human history has witnessed or imagined, and for all of it, the field was pointing in the same direction. A direction we now call normal polarity, meaning the same orientation as today, the same direction modern compasses point. This long stable period is called the Cretaceous Normal Superchron, and it stands in the record as proof that the dynamo is not mechanically required to flip at any particular frequency. The superchron happened, and geophysicists have theories about why. Changes in the heat flow at the core mantle boundary perhaps, alterations in the pattern of convection in the outer core, the influence of the massive volcanic provinces that formed during the Cretaceous, but the honest answer is that the deep causes of superchrons are not fully understood. What is understood is that they occur. The dynamo has states. It can be a machine that flips frequently, and it can be a machine that holds one orientation for longer than the human mind can easily contain. The geomagnetic reversal is not an inevitable, rhythmic clock. It is an emergent behavior of a turbulent fluid system, and turbulent fluid systems do surprising things. The name itself carries the history. Cretaceous, from the Latin for chalk, the chalky white limestone that formed from the accumulated shells of tiny marine organisms in the warm, shallow seas of that era. Seas that spread across much of what is now dry land in Europe and North America, leaving behind the white cliffs of Dover and the chalky downs of southern England and dozens of similar formations around the world. The same ocean that was, during the Cretaceous, depositing chalk on its floor and recording the magnetic field in the minerals of its basaltic crust, a double archive of chemistry and orientation, the field locked in place throughout the whole long middle of it. If you hold a piece of chalk, if you hold the actual white material crumbling slightly, the compressed remains of organisms that drifted in Cretaceous seas, you are holding, in a sense, something that formed during the superchron, something that recorded the same polarity we have now. The compass agreed with itself then as it agrees with itself now, and between then and now there have been 183 full reversals, and the world has survived each one. All of this, the counting of reversals, the naming of crons, the identification of supercrons, and their approximate dates, rests on the same fundamental technique that Brunhes-Matuyama was practicing in the 1920s, when he showed that older rocks were systematically magnetized the other way. Paleomagnetism, the science of reading the frozen magnetic memory of ancient stone. It is not a complicated idea, and its simplicity is part of what makes it so powerful. When iron-bearing minerals cool through the temperature at which they become magnetic, the Curie temperature, a threshold unique to each mineral, named for the physicist Pierre Curie, who described it, they lock onto the ambient field like a photograph locking onto an image. The field at that moment becomes the field frozen inside the mineral for as long as the rock remains undisturbed. Hundreds of millions of years later, a researcher can place a precisely oriented sample of that rock into a magnetometer, a sensitive instrument for measuring magnetic direction and intensity, and read back the polarity of the world at the moment the rock cooled. The ancient field speaks through the crystal. What the paleomagnetic record of reversals tells us, taken as a whole, and read in the way Bernard Brunhes and Matuyama first began to read it more than a century ago, is that the Earth has been conducting this long conversation with itself, this slow alternation of orientation, this periodic breathing of north and south, for as long as we have been able to look. The dynamo did not begin with the Cretaceous. It did not begin with the Cambrian. The oldest rocks that have been convincingly paleomagnetically analyzed suggest the field has existed for at least 3.5 billion years, perhaps longer, sustained over nearly the entire history of the planet by the same fundamental process: heat escaping from a cooling core, convection driven by that heat and shaped by rotation, electric currents sustaining a magnetic field, the field guiding and ordering the very convection that generates it, a self-sustaining loop, a self-organized system that has persisted through everything the planet has experienced, through the formation of the moon from the debris of a giant impact in the early solar system, through the slow oxygenation of the atmosphere by early photosynthesizing life, through the great glaciations that froze the planet's surface to the equator, through the extinction events that periodically reset the roster of dominant species, through all of it, the dynamo churning on in the dark 2,900 kilometers down, indifferent to what was happening at the surface. A reversal is not the field stopping and starting again. It is the field in the process of reorganizing itself, the dominant dipole pattern temporarily losing its grip while the underlying convection continues. A moment of confusion between two stable states, a transition that takes thousands of years and then resolves into a new stable orientation that may hold for another 100,000 years or another few million years, depending on what the deep fluid is doing, depending on the complex internal dynamics that no external observation can fully penetrate. The transition is real, the weakening is real, the multipolarity is real. But it is a phase. It has always been a phase. It ends. And what follows it is another era of stable polarity, another long chapter in which compasses agree with each other, in which migrating animals find their ancient roots, in which the magnetosphere holds its familiar shape above a world going about its business. The Brunhes chron has been going on for approximately 780,000 years. Before it came the Matuyama chron, reversed polarity, lasting about 2.5 million years. Before that, the Gauss chron, normal again, then the Gilbert chron, reversed, and so on back through time, the crons named for scientists who helped piece together the record. Each name carrying a human story of curiosity and careful measurement and gradually accumulated understanding. Carl Friedrich Gauss, the same Gauss who established the first network of magnetic observatories in the 1830s, who gave us the first systematic global picture of the field's strength and direction in his own time, has a chron named after him. A stretch of normal polarity from roughly 3.6 to 2.6 million years ago. William Gilbert, whose De Magnete of 1600 first articulated the idea of Earth as a great magnet, has no chron named for him. The naming conventions came later, were standardized through committee and convention. But his insight underlies all of it. The understanding that the field is not a local phenomenon, not a property of certain special places on the surface, but a global one, arising from somewhere deep inside the planet, a property of Earth itself. Imagine it this way. You are sitting somewhere comfortable, in a room, at night, surrounded by ordinary things. Beneath you the crust extends down perhaps 30 kilometers before giving way to the mantle. Beneath the mantle, 2,900 kilometers of solid and plastic rock, slowly convecting on timescales of millions of years. And beneath that, beginning at a depth that is nearly half the radius of the planet, the outer core, a shell of liquid iron nickel, 2,200 kilometers thick, flowing, not gently flowing, not the way water flows in a quiet stream, but turbulently, driven by convection cells that spiral because of the planet's rotation, by the Coriolis effect, bending every rising column of hot metal into a helical path, the whole vast churning ocean of iron generating currents that generate fields that guide more currents in, the self-sustaining loop that is the geodynamo. You cannot hear it, you cannot feel it. The surface you are resting on is insulated from it by nearly 3,000 kilometers of rock that conducts its heat upward only in geological time, slowly, imperceptibly, a warmth you will never feel directly from the core, though geothermal springs and volcanic vents are its distant surface expressions. The outer core is as remote from your experience as anything can be, while still being part of the same planet you are breathing on. And yet it is not disconnected from you. The field it generates threads up through all that rock, through the crust, through the air, into the space above the atmosphere, where it bends the paths of charged particles streaming in from the sun, deflecting the solar wind away from the surface, protecting the upper atmosphere from the erosion that would otherwise strip it away over geological time, the way Mars, which lost its dynamo early in its history, lost most of its atmosphere. The field is the reason the air above you remains thick enough to breathe. It is the reason the planet has held its water. The geodynamo, 2,900 kilometers down, in a place where pressures are more than 1 million times the pressure of the atmosphere at the surface, where temperatures exceed those at the surface of the sun, where iron is liquid despite that heat, because the pressure raises its melting point high enough that even those temperatures cannot overcome it. The geodynamo, in its restless churning, keeps the surface livable. And it reverses, every few 100,000 years, on a schedule that is not a schedule, with a duration that runs into thousands of years of transitional confusion, it reverses. The poles swap, the stripes on the ocean floor record the swap, the lava and the sediment lock in the new direction, and then the field settles again and carries on. As it always has, as it has for most of the history of this planet, protecting the surface in its invisible way, guiding the creatures that can feel it, holding the magnetosphere in place above an ordinary, quietly persistent world. The creatures that have lived through these transitions, and there have been many through the 183 reversals of the past 83 million years, have generally not left any record of struggle. The plants did not stop growing. The marine organisms did not abandon their shells. The species whose lineages cross the boundaries between magnetic crons emerge on the other side of those boundaries, continuing to be themselves, continuing to evolve along the lines they had been following, not deflected into extinction by the altered field, not driven to new forms by radiation stress that left any visible mark in the bones and shells they eventually became. The story of geomagnetic reversals is in the end a story of deep continuity, of a planet that changes its magnetic mind hundreds of times and barely flinches at the surface. The reversals are written in the rock as dramatic events, boundaries, sharp transitions, the moment the stripes change their polarity, but they are dramatic only at the scale of geology. At the scale of a life, even a long one, they are invisible. They unfold in a silence and a slowness that makes everything else in human experience seem brief by comparison. There is something calming in that, once you sit with it long enough. The field has done this before, many times, in conditions that were, at the surface, sometimes far more extreme than today during ice ages, during warm periods when sea levels were much higher, during times of volcanic eruptions large enough to reshape the chemistry of the atmosphere. And through all of it, the dynamo kept running, kept generating its field, kept reversing and recovering, and settling into new, stable phases. The compass that points north tonight is pointing where it points because 780,000 years ago, the outer core finished a reorganization that had been underway for perhaps thousands of years, and the new polarity it settled into happens to be the one we call normal. In another 780,000 years, or in 50,000, or in 2 million, no one can say. It may settle into the other orientation, and the compass will point the other way, and whatever is alive on the surface will navigate as best it can through the transitional centuries and then adapt to the new normal, as everything always has, because the field is not a threat to life so much as it is a feature of it, a component of the planetary system in which life has always existed. Changing over time, yes, but changing on timescales that make the word change almost misleading, almost too active, and sudden a word for something this patient and this slow. The Cretaceous normal superchron lasted 40 million years. Think of that again, not as a number, but as a silence. 40 million years of the same polarity, the same direction. The same steady, invisible architecture overhead. Whatever existed beneath that field during those 40 million years, and the Cretaceous was a time of extraordinary biological diversity, of enormous dinosaurs and elaborate ecosystems, of the first flowering plants and the insects that co-evolved with them, of shallow inland seas and warm polar regions. None of it knew or required the field to be stable. But it was. For 40 million years it simply held. And then, around 83 million years ago, the dynamo found its way back to reversing, and the field began to flip again at what, by geological standards, might be considered a normal pace. And the creatures of the late Cretaceous and the Paleogene and every era since have been living with that resumed pattern of reversal ever since. The record is there to read. The stripes are there on the ocean floor, symmetric and patient, waiting in the dark beneath miles of cold water, recording every flip, every recovery, every long era of stability, and every dense cluster of rapid transitions. The lava flows are there in France, near the village of Pontferrain, where Bernard Brunhes first found reversed magnetization in 1906, holding their old memory like everything old stone holds memory, quietly, without advertisement. The sediments at the bottom of deep ocean basins are there, their magnetic minerals settled and preserved in sequence, offering continuous records of the field's direction across millions of years without the gaps and uncertainties that come from only studying volcanic rock. The geomagnetic timescale, the organized record of all the crons and subcrons and supercrons, the comprehensive map of when the field was normal and when it was reversed, extending back through hundreds of millions of years, is one of the quiet achievements of 20th century science, built from the accumulated work of researchers on every continent. Using instruments that measure magnetic fields in carefully oriented rock samples pulled from cliffs and ocean drill cores and ancient lava plateaus. It is a diary, a long, slow, faithful diary of the outer core, written in the language of orientation, in the language of north and south, in the only language the minerals know. And we are, as a species, very new readers of that diary. Bernard Brunhes read the first entry only a little more than a century ago, and the full scope of the record, the understanding that the field has reversed hundreds of times over the age of complex life, has come only in the last 60 or 70 years, built on the seafloor mapping of the mid-20th century and the paleomagnetic surveys that followed. We have been reading the diary for a remarkably short time, and already we have learned more about the inner history of this planet than all previous human generations combined could have imagined possible. What we have not learned yet, what remains genuinely, honestly open, is what the field is doing right now, at this particular moment in the long periodicity of reversal history. The last full flip was 780,000 years ago. The field has been weakening, slowly, since systematic measurements began in the 1830s. There is a region of unusual weakness spreading over the South Atlantic. The magnetic North Pole is drifting faster than it used to, fast enough that the maps that govern navigation have had to be updated ahead of schedule. Whether these are the early murmurs of an approaching reversal, or whether they are simply the ordinary variation of a living system that has always wobbled and shifted and breathed without completing a flip, is a question the current science cannot answer with confidence. The honest answer is, we do not know. And before the full weight of what that uncertainty means can settle in, before the question of the South Atlantic and the wandering pole and the weakening field can be placed in its proper context, there is one more chapter to carry in from the past, one more event to understand, an event much more recent than the Brunhes-Matuyama reversal and much more precisely documented, an event that happened close enough to our own time that it has left its fingerprints in ice cores and tree rings and the carbon atoms of ancient wood. An event that was not quite a reversal. Something stranger, in a way, a reversal that started and then changed its mind. 41,000 years ago, give or take, the field began to do something unusual. It did not reverse, not fully. What happened instead was something that the geological record has preserved in exquisite, almost uncomfortable detail. A wobble, a near miss, a moment in which the planet's magnetic field gathered itself as though preparing to complete a full polarity swap, and then, after a period of profound weakness and wandering, pulled back, recovered, returned to the orientation it had maintained since the Brunhes-Matuyama reversal 600,000 years before. And in doing so, it left behind one of the most precisely documented magnetic events in Earth's history. The event takes its name from a village in France. Near Laschamp, in the Auvergne region, there are ancient lava flows, volcanic rocks, cooled and solidified long ago, preserving inside them the direction in which the magnetic field was pointing at the moment those rocks passed through the Curie temperature and locked their mineral grains into permanent alignment. When geologists examined those flows, they found something that should not have been there. a magnetic signature pointing in the wrong direction, not quite reversed and not quite normal. A wandering and disoriented recording of a field that had, at that moment in time, lost its sense of which way was which, and dating those flows placed the event at roughly 1,000 to 42,000 years ago. 1,000 years. In geological terms, that is yesterday. In human terms, it falls squarely within the time of our own species. Anatomically modern humans had been present in Europe and Asia for tens of thousands of years. By that point, painting caves, crafting tools, navigating the world with minds that were, in all the ways that matter, indistinguishable from our own. The Laschamp excursion is not an event from before our story. It is an event from within it, and the field during that event became very nearly nothing. The evidence for the scale of the collapse comes not only from the lava flows near that French village, but from a remarkable convergence of archives scattered across the planet. When the geomagnetic field weakens, it loses some of its ability to deflect the stream of high-energy particles arriving from outside the solar system, the cosmic rays, moving at extraordinary speeds, that the magnetosphere ordinarily diverts before they can reach the lower atmosphere. When more of those particles penetrate, they collide with atoms in the upper atmosphere and produce what are called cosmogenic isotopes. Two of them are particularly useful as fingerprints. One is beryllium-10, produced when cosmic rays strike nitrogen and oxygen in the stratosphere and troposphere. The other is carbon-14, the same radioactive carbon whose predictable decay rate underlies radiocarbon dating. It too is produced in greater quantities when the shield above weakens and cosmic radiation floods in more freely. Both of those isotopes spike in the Laschamp record. Ice cores drilled from the Greenland and Antarctic ice sheets, which preserve annual layers of atmosphere going back hundreds of thousands of years like a stack of frozen newspapers, show the beryllium-10 concentration rising sharply around 1,000 years ago. A clear, unambiguous signature of a field that was no longer fully doing its job. The carbon-14 record shows the same thing. The sky was different during Laschamp. More radiation reached the surface. The isotope ratios in the atmosphere shifted, and those shifts were preserved in ice, in sediment, in anything that was growing and absorbing carbon from the air during those centuries, including, extraordinarily, in trees. In the wetlands of New Zealand, buried in ancient swamp deposits, there exist the preserved remains of kauri trees, a species that still grows in New Zealand today, sometimes reaching enormous size and extraordinary age, but whose subfossil ancestors, preserved for tens of thousands of years in waterlogged peat, have become something no one anticipated, an archive of the ancient atmosphere. Some of these buried kauri are more than 40,000 years old, their wood still intact, their rings still countable. And because each ring records the carbon-14 ratio of the air in the year that ring grew, the kauri trees carry within them a precise, year-by-year account of how the atmosphere changed during the Laschamp excursion. A record that has allowed researchers to calibrate the event with a precision that most geological phenomena of that age cannot approach. The field, at the lowest point of the Laschamp excursion, dropped to something in the region of 5% of its current strength. 5%. Imagine a lighthouse whose beam has been reduced to the faint glow of a single candle, still technically present, still technically producing light, but offering almost none of the protection and guidance that the full beam provides. For a period that lasted on the order of a few centuries to perhaps 1,000 years, the planet was essentially magnetically naked, its shield so diminished that the geometry of the Van Allen belts would have changed dramatically. The aurora would have appeared at latitudes far closer to the equator than it does now, and the surface would have received a measurably higher dose of cosmic radiation than at any point in recent human history. And then the field recovered. It did not complete the reversal. It pulled back, restabilized, returned to something close to its prior orientation. What had looked, for a period, like the beginning of a full polarity flip turned out to be, in the long accounting of geomagnetic history, a false start, an excursion rather than a reversal. The poles had wandered far, the dipole had collapsed, and then the system had reasserted itself. In 2021, a group of researchers proposed a study, published in the journal Science and attracting considerable attention, that attempted to link the Laschamp excursion to a cascade of environmental and evolutionary events occurring around the same time: changes in megafauna populations, shifts in vegetation, developments in human behavior. This interpretation, sometimes called the Adams transitional geomagnetic event, is a contested one. The specific claims that the magnetic weakening drove or amplified particular ecological changes are not established scientific consensus, and the causal connections are genuinely disputed among specialists in paleomagnetism, paleoclimatology, and archaeology. The excursion itself is not in question. The isotope spikes are not in question. The dramatic weakening of the field is documented. But the idea that the weakening set off a chain of catastrophic consequences for life on Earth is, as of the time the evidence was assembled, an open debate rather than a settled finding. What is not debated is the simpler, quieter truth. The Laschamp excursion happened. Life continued. Our ancestors were present during it, and whatever challenges they faced, and the world of 1,000 years ago was already a harsh one. Ice Age Europe, megafauna sharing the landscape with early modern humans, the climate fluctuating in ways that had little to do with magnetic fields, the species survived. The Laschamp excursion did not end us, and it was, in terms of field collapse, far more dramatic than anything recorded in the current era. That is worth sitting with. The field fell to 5% of its current value. The sky changed. Isotopes spiked in the ice and in the wood of ancient trees. And we are here, continuing, carrying the story forward. The planet turned another page, and now we come to the page that is currently open. The magnetic North Pole, the point on Earth's surface toward which a compass needle's northern end is drawn, the wandering intersection of the field's axis with the planet's outer skin, has been drifting for as long as systematic measurements have been made. It has never been perfectly still. But in recent decades, the drift has accelerated in a way that has attracted sustained attention from the scientific agencies responsible for maintaining the navigational charts that modern aviation, maritime travel, and GPS systems depend on. Through much of the 20th century, the North Magnetic Pole moved at a rate of roughly 15 kilometers per year, and it moved in a direction that carried it gradually away from its position in the Canadian Arctic. That pace was manageable. The World Magnetic Model, the international standard used by navigation systems and electronic compasses worldwide, was updated every 5 years as a matter of routine, and the corrections required were modest and predictable. But toward the end of the 20th century and into the early decades of the 21st, something changed. The pole began moving faster. At times its drift rate reached 50 or 60 kilometers per year, several times what it had been. The World Magnetic Model had to be updated ahead of schedule, an event unusual enough to draw notice, because the pole was moving quickly enough that navigational errors could accumulate before the next planned correction cycle. The pole is now moving towards Siberia. It left the Canadian Arctic. It crossed the international dateline. It is, as of the most recent measurements, somewhere in the Arctic Ocean, continuing its eastward drift toward the Russian side of the pole, and the question of where it will be in another decade is genuinely uncertain. The field's behavior at depth, in the outer core where the geodynamo is churning, is what drives the pole's surface wandering, and the outer core is not visible. Not directly measurable, only inferred through the patterns its field imprints on the surface above. But the patterns have changed, and the pole is moving, and the agencies responsible for keeping navigational maps accurate are watching. The acceleration of the pole's drift is thought to be connected, at least in part, to changes in the flow patterns of the liquid outer core. A kind of jet stream deep inside the planet, a fast-moving current of molten iron running beneath the northern latitudes of the core, whose influence on the surface field appears to have been strengthening. But this is an active area of research, and the mechanisms connecting deep core dynamics to surface magnetic behavior involve layers of complexity that even sophisticated models have not fully resolved. The core is far away. It is unreachable. It speaks to us only through the field it generates, and reading that field carefully enough to understand the motions producing it is something scientists are still learning to do. Meanwhile, the field itself, taken as a whole, has been weakening. Carl Friedrich Gauss, the German mathematician and scientist, established the first network of magnetic observatories in the 1830s. A coordinated set of stations designed to measure the strength and direction of the field at multiple locations simultaneously, providing for the first time a basis for systematic global monitoring. Before Gauss, measurements existed. Sailors had been recording magnetic declination for centuries, noting the difference between magnetic north and geographic north at various points across the ocean. And those records have proven useful to later researchers, but Gauss gave the science a methodological foundation. And from those 1830s measurements forward, a continuous record has been built, station by station, decade by decade, extending into the satellite era and becoming progressively more detailed and more global in coverage. That record shows a decline. The overall strength of the dipole, the dominant bar magnet-like component of the field, has fallen by roughly 9% since Gauss's time. 9% over approximately 170 years. It is not a catastrophic drop. The field remains strong enough to do its job, strong enough to sustain the magnetosphere, strong enough that a compass still points reliably north nearly everywhere on Earth. But the trend is real, and the question of whether it represents the beginning of something larger or simply the ordinary breathing of a system that has always varied is one that cannot yet be answered with confidence. And then there is the South Atlantic Anomaly. It is, in the vocabulary of geophysicists, an anomaly, a region where the field departs significantly from what models would predict for that location. It sits over the South Atlantic Ocean, stretching roughly from the coast of South America eastward towards southern Africa, a large and irregularly shaped region of unusual weakness. Within this region, the inner Van Allen radiation belt, one of two zones of energetically charged particles trapped by the magnetic field and normally held well above the orbits of low Earth satellites, dips unusually close to Earth's surface. The field above the South Atlantic is not strong enough to hold the radiation belt as high as it is held everywhere else, and so the belt sags. And anything passing through the airspace above the South Atlantic Anomaly passes through a region of elevated radiation that is, under normal circumstances, confined to much higher altitudes. The practical consequences of this are not theoretical. They are measured. The Hubble Space Telescope, whose instruments include detectors sensitive enough that stray particle hits would corrupt the data, does not conduct scientific observations when its orbit carries it over the South Atlantic Anomaly. It passes through, and it waits, and then it resumes. The International Space Station, whose crew is monitored for radiation exposure, accumulates a disproportionate fraction of that exposure during passes over the anomaly. Satellites in low Earth orbit log a higher rate of single-event upsets over the South Atlantic, moments when a passing particle strikes a memory cell or logic gate and flips a bit, causing a transient error in the spacecraft's electronics. These are not disasters. They are managed. Engineers know the anomaly is there and design systems accordingly, but they are real, measurable departures from the baseline, caused by a real, measurable weakness in the field above a particular region of the planet. And the anomaly appears to be growing. The European Space Agency's SWARM mission, a constellation of 3 satellites launched in 2013 specifically to map the geomagnetic field with unprecedented precision, has been watching the South Atlantic Anomaly for years. What the SWARM data shows is that the region of weakness is not static, it has been drifting westward, and it has been expanding, and there are indications in the data that it may be developing a second center of weakness, a secondary lobe forming over Africa, separate from the original lobe centered over the Americas. Whether this represents the early stages of the anomaly splitting into 2 distinct regions, 2 separate bruises on the planet's magnetic skin, or whether it is a temporary feature that will merge back or stabilize or dissipate is not yet clear. The SWARM satellites are still gathering data. The models are still being refined. The anomaly is still evolving. Whether the South Atlantic Anomaly, the accelerating drift of the magnetic North Pole, and the 9% weakening of the dipole since the 19th century represent the opening act of the next full polarity reversal, or whether they represent something far less dramatic, a particularly active phase of ordinary variation. Perhaps the beginning of an excursion that will recover as Laschamp recovered. Is, with complete and honest clarity, unknown. It is tempting, when looking at those data points assembled together, the weakening field, the wandering pole, the spreading anomaly, to feel the pull of pattern recognition, to sense a narrative building toward a conclusion. The human mind is extraordinarily good at finding stories in data, at constructing arcs with beginnings and ends, at reading trend lines as prophecy. But the geomagnetic field does not obey the expectations of narrative. Some researchers, comparing the current state of the field to the signatures of past reversals preserved in the paleomagnetic record, have noted that the present configuration does not clearly match what has been observed in the approach to previous flips. The dipole, though weakened, remains well within the range of variation that has characterized the Brunhes-Matuyama across the last 780,000 years. There is no consensus that a reversal is coming, and no scientific basis for predicting when the next one will occur. The honest answer, stated plainly, is that we are watching a living system in motion, and we do not yet know what that motion means. We have had, in the grand span of planetary history, a very short time to watch. Gauss gave us roughly a century and 3/4 of continuous instrumental data. The satellite era, which has provided the most detailed global coverage, spans only decades. The Swarm mission has been operating for little more than a decade. Against the backdrop of reversal timescales, intervals ranging from tens of thousands to tens of millions of years, our instrumental record is a single breath. The field has been doing this for billions of years, and we have been paying careful attention for less than 2 centuries. What we can say is this: the machine is running. The outer core is churning. The molten iron-nickel ocean is convecting and spinning and generating its vast, slow electrical currents. The solid inner core, at the center of everything, is still growing outward by a fraction of a millimeter each year as iron crystallizes onto its surface at pressures that no material on Earth's surface ever experiences, releasing the compositional buoyancy that helps drive the system, powering the geodynamo through geological time. The field that this machine produces has reversed hundreds of times, each reversal preceded by a weakening and a wandering, each transition lasting thousands of years, each one navigated by the life on the surface above without catastrophe, without a single mass extinction that can be traced to the magnetic shift rather than to the independent vagaries of climate and impact and volcanism. The field has wobbled and excursioned and recovered. The compass has been confused before in the frozen record of ancient lava flows and recovered. The sky has been more open to the cosmos before, in the isotopes archived in ice, and in the rings of trees that are now subfossil wood in a New Zealand swamp, and life continued. And we are the first ones who can read any of it. There is something worth pausing on in that. Every other species that has lived through a geomagnetic reversal, the trilobites of the early Paleozoic, the dinosaurs that walked through several flips without incident, the early mammals that experienced the Brunhes-Matuyama boundary 780,000 years ago, the archaic humans who were present in Africa and perhaps Eurasia as that transition played out, every one of them lived inside the story without knowing the story existed. The birds still flew, the turtles still navigated, the whales still found their way through dark ocean water. They did so by instinct and adaptation, unaware that the invisible force they were relying upon was itself in flux, that the signals they were reading were the outputs of a machine they could not conceive, and that no mind on the planet yet had the tools to imagine. We are different. Not better, necessarily. The question of whether it is better to know or not to know is one that the universe does not answer for us. But different. We have spent centuries, beginning in a formal sense, with William Gilbert sitting in his study in London in the year 1600, writing out in careful Latin his argument that the Earth itself is a great magnet, and extending through every magnetic observatory and every paleomagnetic laboratory and every satellite launched to map the invisible architecture of the field, we have spent centuries learning to read what the planet has always been doing. We can look at a stripe of seafloor basalt and know which way north pointed when that rock cooled. We can drill into a Greenland ice sheet and find a spike in beryllium-10 and know that 41,000 years ago, for a few hundred years, the sky was more open and the cosmos was closer. We can read the rings of a kauri tree that has been lying in a swamp since before the last ice age reached its maximum extent, and find inside that wood the carbon record of an ancient atmosphere. We are, for the first time in Earth's history, a species capable of hearing the planet's magnetic heartbeat. The diary has been kept for billions of years. We have been reading it for a very short time, and what it tells us so far is not a story of catastrophe, it is a story of continuity. The field breathes. It has always breathed. It will weaken and wander and perhaps eventually reverse. And when it does, the transition will unfold over thousands of years, not overnight. The field becoming messy and multipolar and temporarily confused, the compass pointing somewhere unreliable, the aurora blazing at unexpected latitudes, more cosmic radiation reaching the surface, the Van Allen belts reconfiguring themselves for a planet with a different orientation. And life will navigate it, as it has always navigated it, adapting to what changes, relying on whatever cues remain, finding its way through the transition and into the next stable period on the other side. We are not at the end of something. We may be in the middle of something, or near the beginning of something, or simply in the ordinary middle of a long stretch of variation that resembles many other long stretches in the paleomagnetic record. The South Atlantic Anomaly is widening, and the swarm satellites are watching it, and the scientists studying the data are appropriately uncertain about what it means. The pole is racing toward Siberia at speeds that would have seemed alarming to Gauss if he could have imagined them. The field has been declining since his observatories first began their vigil, but the field is still there. Above this room, above this moment, the magnetosphere is doing what it has done for billions of years, curving outward into space, deflecting the solar wind, carving out the protected bubble inside which this particular planet has assembled its particular chemistry of life. The compass still points north. The birds still know where south is. The turtles still find their ancient beaches. The whales still sing their navigational songs into dark water. The machine at the center of the earth is still running. There is, in the accumulated record of reversals and excursions and supercrons and wandering poles, a kind of deep reassurance available to anyone willing to stay with the timescale long enough to feel it. Not the false reassurance of denial, the field is changing, the measurements are real, the uncertainty is genuine, but the reassurance of proportion. A reversal, when it comes, will take 1,000 years or 10,000 years to complete. No one alive today, and no one alive for many generations yet, will experience anything more than the slow, incremental continuation of what is already being measured, a slightly weaker field, a pole that has wandered a few hundred kilometers further from where it was. The drama of a full polarity flip, a compass pointing south, multiple magnetic poles appearing simultaneously across the globe, the aurora blazing at equatorial latitudes, is not a drama on a human timescale. It is a drama on a geological timescale, and on that timescale it is not catastrophe, but rhythm. The planet has its own breathing, its own pulse. We are too small and too brief to feel it in our bodies, but we have built instruments sensitive enough to detect it, and we have found the archives in which it has recorded itself, and we have learned to read them. That is not a small thing. That is one of the stranger and more beautiful achievements of this particular species on this particular planet. The capacity to sit down with a striped map of the ocean floor, or a drilled cylinder of ancient ice, or the preserved wood of a tree that has been lying in a swamp for 40,000 years, and reconstruct from those silent materials the movements of a machine 6,000 kilometers below your feet. You are lying here, perhaps, in a room that is dark and quiet, and the field is above you and below you and all around you, passing through the walls and through the floor and through everything in between without friction or sound. A shape drawn by the churning of liquid iron at a temperature and pressure so far outside ordinary experience that no analogy quite captures it. The compass needle in any compass in this room is being pulled, right now, by the same invisible architecture that has been pulling needles since long before there were needles to pull, since long before there were hands to hold them. since before there were creatures with eyes to see which direction the needle pointed. The field does not know we are here. It is not watching us. It is simply doing what it has always done, running the machine, tracing the dipole, drifting and wandering, and occasionally, over the vast unmeasured years, flipping from one orientation to another and back again, as it has done hundreds of times, as it will continue to do long after every instrument we have built to measure it has corroded back into the earth and been incorporated into rock. That will itself, over millions of years, be subducted back into the mantle and melted and recycled, and perhaps one day brought up through a mid-ocean ridge and spread across the seafloor and cooled and locked into the orientation of whatever field is present at that moment, adding another stripe to the barcode, preserving another quiet record of which way north was pointing on a particular day, in a particular era on this particular planet. If you feel moved to share where you are listening from tonight, I would genuinely like to know. The comments are there, and I read them. There is something fitting, I find, about knowing where in the world each listener is resting, each one lying inside the same field, each needle in each compass in each room pointing toward the same wandering pole, each person held gently inside the same invisible machine. There are more stories here of the same slow and careful kind, waiting for whenever you want them. And for now, for this particular night, this particular hour, this particular moment in which you have come to the end of this long descent into the deep history of the compass that keeps flipping upside down, there is nothing more to carry. The machine at the center of the earth will keep running without your attention. The field will keep finding its shape. The pole will drift a little further toward Siberia by morning, a few tens of meters in the dark, and you will not feel it. The South Atlantic Anomaly will spread a little further over the ocean, imperceptibly over months and years and decades. And the satellites will keep watching. And the scientists will keep reading the data, and the questions will stay open, as questions are supposed to stay open, until the evidence speaks clearly enough to close them. The diary will keep being written. We will keep learning to read it. Let the deep thoughts settle, and let yourself sink with them.